Thank you everyone for joining us today for our distinguished speaker. We have with us today Dr. Mashrur Ronnie Chowdhury. He's the Eugene Douglas Mays Professor, as well as our Center for Connected Multimodal Mobility Director. And he also teaches automotive engineering and in computer science at Clemson University. So Dr. Chowdhury, as well as teaching, is the co-director of the Complex Systems Analytics Visualization Institute, so SC-CVT, and his experience in research includes transportation, cyber-physical systems, security, navigation of connected and automated vehicles through in-vehicle sensors, and external connectivity with digital infrastructure, heterogeneous wireless communications for security, distributed machine learning on the edges, and other edge computing applications, as well as safety risk analysis for autonomous vehicle operations in mixed traffic. So Dr. Chowdhury's published over 100 peer-reviewed journal papers, 85 peer-reviewed conference proceedings, 4 textbooks, 9 book chapters, and several research articles widely circulated in professional magazines. So we're very excited to hear him speak today on the public digital infrastructure deployment for future mobility.
Good afternoon, all. So I'm very excited to be able to talk to you about digital infrastructure. I'm a big proponent, supporter of deploying public digital system to support future transportation system as well as smart cities. So I think that we are lagging behind the private industry in mobility systems, mobility technologies. So how we prepare, how we keep pace with the private industry is a great interest of me. So I'll be able to discuss that with you today and share ideas and my thoughts how we should proceed in this area, a very important area. So, and I'm a professor of transportation, and as Charlotte mentioned, I direct the Center for Connected Multimodal Mobility. And if you want more information about our center, here is the website address. So please visit our website address, our website if you have any question or you want to see what we are doing, and you can always email me or Charlotte with any question. So this is what we are envisioning at a high level. So the digital infrastructure for surface transportation. So it will be a distributed system. So there are a couple of main categories of infrastructure. One is the backend. So we can have cloud services. So it could be commercial cloud, or it could be any private servers, like our servers that are operated and maintained by a public agency. And then we have on the left, as a part of backend infrastructure, we have different centers. It could be a DOT or a city or a county traffic management operations center. It could be emergency management center. A variety of centers could be a part of these center systems. So who will be a part of our digital system in transportation. So now this is the back end. Now we have another layer that is a roadside infrastructure. So it could be a traffic signal. It could be any traffic system. It could be a dynamic message signs that provides information to the drivers. It could be a roadside unit. So it could be a DSRC radio, or it could be any 5G access points or LTE access points, Wi-Fi access points. So a variety of communication access points could be as a part of the roadside system. And then you could have different types of sensors. So existing sensors, you have traffic cameras, you could have loop detectors, you could have radar detectors. So any roadway sensors could be a part of your roadside system. And now on the right side, you have connected vehicles, automated vehicles. So the connected vehicles have sensors, in-vehicle network and the software. And then it is communicating with other connected vehicles. Now, this is not a comprehensive set of connected system. You can have connected pedestrians with a cell phone, connecting with your whole system, with your digital system. It could be a person in wheelchair connected to your system so that we can help the person in wheelchair to navigate the transportation system. So it could be any connected mobility devices, scooters that are connected with your back-end system and roadside system. So it is a connected world. So all the connected devices, connected vehicles, connected pedestrians, so all are connected to your digital system. And as I go forward, some of the things that we are discussing, so you can see at the bottom, the citation where this information is coming from. So you can see the citation of the source. So now after, so this is our high-level digital infrastructure. Now the backend could have different layers depending on the complexity and how much scale up you need to do based on the penetration of vehicles or other transportation modes. So you can scale up to different layers of backend system. So this is what we are envisioning. So we have this digital system infrastructure that we need to deploy. Public agency will be deploying these systems in collaboration with private industry, because those will be in the public land. So there needs to be a public-private partnership. And then this is on the left side is a new and refurbished transportation system. So we have this existing transportation infrastructure, freeway, bridge, transit port, street, any other, say airport. But so, and on this system, we have our legacy system, like we have a traffic control system. It could be traffic signal. It could be ramp metering. It could be anything that we are currently using. It could be detectors, so on. But when we're trying to go to the next level, we are going towards the connected system, a connected automated system, when we are bringing in a lot of automation in our transportation. So there has to be a perfect marriage between this new, that how we refurbish the current system. For example, if you want to implement adaptive signal control on your corridor, you may need to install new types of sensors or increase the level of sensors or where you're putting the sensor. So you need to refurbish what you have and add new types of devices. So, and this is the digital is what you may already have some system in place. For example, public agencies, especially DOT, has a significant miles of fiber optic connection, fiber optic wires between throughout the state. For example, this is true for South Carolina. So you could use it as a part of your digital system, but you need to augment it with other wireless system, or maybe you need to add some wired communication as well, and deploy computers, back-end computers, deploy servers. So what you have, so we need to look at what we have as a public system, and then see how we can augment that so that we can support the new and refurbished transportation system, and they work together. So there's a perfect marriage. So these two, the digital system and new and refurbished system, so they're added to make the perfect application. So we have different applications that can help us to improve safety, improve mobility, improve environmental sustainability, improve energy consumption. So we are doing this for the purpose of making our system much, much better. So these are some high-level benefits of having a digital system in transportation, the back-end system. So we can have a continuous feedback loop between the physical and cyber systems. So what I'm saying that we are deploying these transportation cyber physical systems, which will be the future of our transportation system. As you look around, we are going more and more towards cyber physical systems. So, and for not only for transportation, if you look at any other system like a smart energy, smart building, so we are going more and more on a smart home, for example, we are going more and more on cyber physical systems, and transportation is a part of it, and it will be a part of it, and the involvement of the transportation as a cyber physical systems will increase dynamically in the next few years. So that is good because we can have a continuous feedback. So this physical system providing data to a cyber system or to computer or computers, and then the computers are processing data and it is providing feedback to your physical system. So you have this continuous feedback that will improve, that will help you to improve your transportation system. And as I said, the ultimate goal is to improve safety, efficiency, and reliability. And we will achieve that through the transportation cyber physical systems. So in terms of legacy systems, we look at traffic signal, traffic signs, and any IT equipment currently the public agencies have, and what we need to do to update those systems. So there needs to be an audit and identify what improvements we need to synergize with our new digital infrastructure that will support our future transportation system. So in terms of a digital system, a backend system, we need to have a look at the communication infrastructure and also the data system. So in terms of the computing resources, what computing resources we need to add, and at the same time also the data analytics, what software we need to have on those computers. Do we need database software? We need to analyze the data, so what software we need to manage the data, to distribute the data. So this will be something new. We may not be able to use what we have been using. So the concept of, we call it big data, because we are getting different types of data from the transportation system. Microscopic data, macroscopic data, some data are coming through streaming, some are historical data, some are coming every 30 minutes or so. So all these different data, and they could be very big in terms of size of data as we have more and more connected devices and transportation modes on our highway. So the way we deal with the computers and the data analytics or software or database, so it will be different. So you'll see that we will need to use different data management system that can handle those big data traits that we'll see in future system. So it should be new types of requirement identification and find out what will meet the requirement. So I'll just highlight some of the challenges we have. So it can come from the policy, technical, and investment. So in terms of the policy challenges, there are lack of financial resources to actually deploy a digital system for transportation. And also right now, we are not actually defining exactly how the digital system in the back end will help transportation. So that will be something that we need to communicate with everyone, that this is very important. This will help us to prepare for the future transportation system. So, and because as we all know, that public agencies are struggling to keep their roads up to the standard, maintaining the roads and bridges and tunnels. So in addition to that, if we are talking about investing in digital system, so that might be a stretch because of financial constraints. So we have to look at innovative ways to do this. But the motivation is private industry, the automobile manufacturers are moving very fast in modernizing their systems, but it will not be an optimal system unless the transportation public system supports it. So in the next point, lack of harmonized deployment strategies. So what we see today, it's actually not harmonized. So for example, when we are making our signal system connected, at the same time, we need to develop our backend infrastructure that can also support other systems. Like if we want to implement collision avoidance, if we want to do any other application through connected vehicles, we need to do that. So when we develop our system, there has to be a plan that, okay, we are developing in a stepwise fashion. So what comes first? So we know that we have to have this communication. So we need to first, if you're trying to deploy our digital system on a corridor, we need to prepare the back end. So do we need to install more fibers? We need to have wireless communication actually installed on some of the transportation components. The next point is a lack of coordination between public agencies and private sector. So that comes to the first point, lack of financial resources. I see there will be a need of public-private partnership, because we'll be relying on a lot of the communication system these telecommunication companies have. For example, 5G will be a major part of our future connected system. So how we take advantage of that, that will require a coordination between public and private sector. So legal implications is important. So we have to look at the liabilities. If we are providing collision avoidance information or any other warning, so what are the legal implications? So that needs to be looked at. In terms of technical, as I mentioned earlier, the upgrading the existing system is an important goal. So how we'll support our future backend system by upgrading the existing system. The next item, security and privacy issues will be important. So we need to look at that. And the third point, standardization of technologies so that we can have interoperable systems. So no matter which manufacturers do provide the system, it should be interoperable no matter what type of systems we have. So our detector should be able to talk to the signal controllers and the connected vehicles, connected pedestrians. So we need to look at the standards. So there are already industry standards that we can follow. There are some intelligent transportation system standards that we can follow. But there will be need for new standards so that the systems are interoperable. So the last point in technical, that is we have to have an understanding of heterogeneous wireless networks because based on where the vehicles are, where the pedestrians are, and it's dynamic system, they're moving from one zone to another zone. For example, if we have a 5G coverage for a section of the road, we may not have that coverage when we go beyond that 2-mile stretch. So what communication option we use and how we can hand over from, how we can perform the handover function from 5G to LTE or from LTE to Wi-Fi. So, and that will depend on a lot of different factors, the application requirements and the coverage, the signal strength and access points. So this needs to be understood very well, and we need to implement this heterogeneous wireless networks for efficient communication. Now, in terms of the last category, investment, agencies responsible for deployment should leverage the national ITS architecture. And also we have several pilots ongoing on connected vehicles and smart city pilots. So we should learn from those deployments. So for the connect pilot programs on CVs and smart cities. And I mentioned the ITS architecture. I will show that soon, but I feel that's very important because that gives a starting point for public agencies to see what's out there, what they can achieve, what are the standards available, what should be the data exchange between different transportation systems, whatever backend system they will need. So my previous employer was Iteris, and Iteris actually developed this national ITS architecture, and then we had this connected vehicle reference implementation architecture, CVT. So now they combined this national ITS architecture and CVT, and they call it ARKit. So but that's a very good resource for any agency to look at that and see that what's there. It's a very high-level architecture, but and how we can go to the deployment level from the architecture. So, and when I deployed any systems here in Clemson or in other locations, I always look at the architecture. For example, when we decided to deploy queue warning on a road in Clemson, I looked at the architecture first, because that provides a very, very good guideline. When I did the speed advisory using commercial cloud, my first destination was this Archite website. And then the next point, public agencies should have some type of benefit cost analysis, so they can see that what the benefits they will gain from deploying the digital system to support future transportation. And as I said, it comes from the policy perspectives as well, that we need to find ways for non-technical funding sources. It could be resource sharing in a different way. So we need to go beyond the fuel tax and tolls to fund this future digital system for transportation. Okay, so this is a good resource. As I mentioned, any application I develop, I deploy, always look at the ARKit. So I teach ITS class, connected vehicle class, autonomous vehicle courses. The first I communicate is this ARKit, because this provides them a very good guideline on building the system. So this is the first step that we should look at. And then in the ARKit, so they have different I'll just go back to the previous slide. So they have these different views of ARKit: enterprise view or the business view, functional view or the logical architecture, physical view looks at the physical architecture, and the communication view. So these 4 views gives a very good indication how we should start the project, the deployment project. So, and they have over 100 applications in different areas in safety, with connected vehicles, with mobility, for environmental sustainability. And it's categorized by these different areas, and you can see what applications are there. So here we see dynamic eco-routing, eco-traffic signal, connected traffic signal. So electric charging, station management. So this is looking at the environmental sustainability application, but for mobility application, you can see how we can manage congestion, so on and so on. So now I will share some of our experience in real-world digital system deployment, digital infrastructure deployment. So first, we start with architecture. So we refer to the ARKit as the first very high-level architecture, and then we develop a detailed architecture from that for digital infrastructure design. And then we do the system design. Then we develop a prototype in a control environment. So we test the prototype. Prototype is a combination of software and hardware that help us to achieve the functions of the application. So we do the prototype development and testing in a control environment. Then we develop in the real world. That means on a roadway, on a highway, on a freeway. So then after we are satisfied with the prototype, then we deploy in the real world. And then we validate the application. So we are validate in terms of the design. So so we are achieving the same type of results as we achieved in the prototype, because now we have the real world transportation system, moving vehicles, pedestrians, and so on. So validation, we look at the impact of the application, or what the measures of effectiveness changes from before and after. So for example, we look at whether it improves safety between before and after, whether it improves speed of vehicles, whether it improves pedestrian safety. So we validate our application in the real wall scenarios. So our architecture, the second level architecture. So first we looked at the ARC-8, and then we looked at more detail how we are going to implement our connected vehicle, connected autonomous vehicles, digital system. So we go over this architecture in a layered fashion. So we have this at the lowest level, we have the mobile edge, and then we have the fixed edge, that is the roadside edge, and then we have the server edge. So this is showing a 3-level, but it can be the levels could be more. So the system edge could the fixed edge could be many. It could be more layers. So as the server layer, it could be many sub layers depending on the complexity of the transportation system, as well as how many transportation components we're expecting, how many connected vehicles we're expecting, how many pedestrians will be at that intersection. So based on those application requirements, it could be changed, it can be scaled up. So you should have the opportunity to scale up. And then we are here, the communication is using DSRC. For one of our applications, we were using DSRC, but it could be any other wireless communication link. You can use 5G, you can use any other communication options that satisfy your application delay requirements and the band throughput requirements. Then for our application, we had, so the LT, we have our own LT stations that were linking to our system edge. So the mobile edge and fixed edge were linked to the system edge, so which is a server. So through LT. Now you can use, so in our case, we use our own LT stations, but you can use the commercial LT services as well. And the cloud here, the system edge, it could be a commercial cloud, or it could be a server that our agency owns, or our university owns, or the DOT owns. So, but I see a great value for public agency in using commercial cloud. We will discuss that shortly. So now we have the architecture, then we looked at the design. So this is not showing at a detail like what type of codes we have for each of these. It's showing a high level system design. So the mobile edge, we have the message broker, which is managing the distribution of messages. So, so we have MQTT broker. We can use Apache Kafka and any other broker system. And then this is where it's running the application. And this mobile edge will include, say, if you can think of a box, it will include a radio interface, and it will can have a computing device. In our case, we use NVIDIA TX2 device for computation, running the application. And then you have the heterogeneous wireless communication handover management. So it is looking at what are the access points the vehicle can see through the radios, and it will decide that what to access. So we have to optimize the loads on the available communication mediums, and then it will choose that based on the signal strength the application needs, where the mobile edge should connect to. Is it LT, 5G, DSRC? So the decision of where to connect will depend on this module, heterogeneous wireless communication module. Then, yeah, so it has the onboard unit for connecting with the roadside unit, RSUs. And then we have this fixed stage that is on the roadside. So again, it has this heterogeneous wireless communication because it will manage handover from one access point to another access point, maybe between a Wi-Fi access point to an LT access point, to a 5G access point. So this is a system that is very important for handover management. So we developed a software that can do this handover management quite efficiently. So for our deployment. And then we have a local data store that it's not a huge database, but it can store some data that is needed for application processing. We also have a message broker because we need to distribute the data and then there's an application running on our computer, TX2 computer. So then we have the system node. It also have the heterogeneous wireless network, because if you're deploying the system at a connected transmission system at a larger level, then our heterogeneous wireless communication network selection stays in the system node, and you'll see in a later slide how they are connected. What is the system node doing in terms of network selection? It also runs an application, and it has a global data store, so it can contain historical data, the real data coming from your mobile edge, and also it has a message broker because we need data distribution. So, and there are multiple fixed edge operating, and there will be multiple mobile edge and different types of mobile edges, right? So it could be vehicles, pedestrians, scooters, connected scooters. So is the roadside units. It will be many. So it could be a roadside unit just broadcasting and receiving data, but it could be a signal that is sending data to vehicles and receiving data from vehicles, a connected signal. So the prototype development strategy, it worked very well for us. So we tested our system in a controlled environment. We also have a test bed in Greenville, but we also have one very close to the campus. So we use that to test our system. So when we developed our collision avoidance system or a queue warning or any other system, we first tested on our in a control environment. It's a student organic farm, as you can see, and we have about 1.5 mile road or 2 miles. So there is rarely any vehicle there. So, and we installed all our roadside devices here. We have connected vehicles, and we have the whole road is controlled. So when we test collision avoidance, so suddenly the vehicle stops. So there will not be any safety implications from other vehicles, not a part of our test. So any prototype we develop, for example, the heterogeneous wireless networking, we first tested here. Now, once we are tested and we are happy, everything worked well, then we have graduated to deploy this 3 mile stretch of road on perimeter road. So we have many fixed edges. As I mentioned, we have on a light pole, we have the TX2 computing device. We have Wi-Fi access point. We have the DHRC access point. And you can see here, we have the LT stations that are also part of our communication network. So, and then we have an extensive backend system. So we have the system edge, and we layer it when we think that we need more sophisticated we need to run sophisticated application. We actually increase the number of system edge, so we can also improve the number, increase the number of fixed edge. One example I would provide how this system edge and mobile edge and fixed edge are working together. So we developed a queue warning application with distributed machine learning. So what was going on? So we were identifying whether there is a queue or just one vehicle stopped just for a random reason. So the major machine learning model, the support vector machine, was running in the system edge, and we were training and verifying the machine learning model by the data received from the fixed edge. So we were retraining. So for example, I will give you like a duration. So every 30 seconds, we were modifying the parameters of our machine learning models. And then we are sending the trained models to the fixed edge to determine whether there's a queue or not. But the main training was occurring at the system edge. And we are only sending the trained functions to the fixed edge to determine the queue. But the advantage of this system is we don't need a lot of computing power at the fixed edge because we can provide that computing capabilities at the system edge for large-scale training and verification, and then we can just send the function. So now all these systems are in place. So we have a fiber optic connection, we have Wi-Fi link, we have DHRC link. So we are now working on deploying 5G. That would be a nice option for low latency communication. So heterogeneous wireless networking option we just provided, we just mentioned. So that could work with any communication options you have. So no matter what system you have, it will work. And also we have developed how you can actually evaluate 5G communication for transportation. So so we have developed some options that how you can see that how well a 5G network will work for communicating with connected devices, vehicles, people, and infrastructure. So this short video I'll show about our testbed and example of what we are doing in the testbed. We have to look at the security in a very comprehensive fashion, that what are the different kinds of attacks can happen and how we can protect against them. Say a vehicle arriving, there are a lot of pedestrian activities. Pedestrians are crossing intersections. So now, so there could be a camera at that intersection looking at the whole intersection, and it's tracking the pedestrians just to identify where pedestrians are, the walking speed, the heading. The video is analyzing the data, sending the data to a roadside device. Roadside device is determining the risk of pedestrians being in the crash path of a vehicle, and it will warn everyone that it's not safe. And we have other mobility devices like very popular now in some cities. So I see that all this pedestrian activity, so with this type of connection, you can make it safer. So on our test bed, so we are doing security validation to how we can make sure that our connected systems are secure. So two major items we should focus on, the computer and network security. So you have these devices, computing devices in your connected system. So how you can make sure that your system is safe, the computer system is safe, and the network. So you look at the security of the network and security of your computer system. And then, so how you can protect if an attack happens on your system, and also make them resilient. How you can make them resilient. So for example, sometimes you cannot help. Attack will happen. And if an autonomous vehicle is attacked, then it could create a lot of problems. There could be a loss of lives and property. So how we can protect the autonomous system, connected autonomous system. So one is that, okay, we identify if there is any attack, but also we need to make the system resilient. So one is protection, countermeasures, and also another item we are looking at is resiliency of the system. So in addition to testing on our test bed, we also test on like large parking lots when they are empty. See, you can see that we are testing cooperative adaptive cruise control. We are testing forward collision avoidance. And this one is adversarial attack on automated vehicle. So as you know, autonomous vehicle controller uses machine learning to make several decisions based on the sensor data. So here you see that that it's actually a stop sign. The video is looking at stop sign, but someone can do an attack on the controller or the AI system, the artificial intelligence, and make it look like it's a 45 miles per hour sign. So there could be a targeted attack or a random attack, but it can change what the vehicle, autonomous vehicle is sensing or seeing. So, and we developed a software to detect such attacks, adversarial attack on AI, and how to mitigate those attacks. So, and we are also doing this on a test bed. So I call them that in order to make sure that our connected transportation is mainstreamed, people need to have trust on the system. So I call it a trustworthy connected autonomous system. So the autonomy and the connection must be trustworthy. So it can be trusted by the industry that, okay, I can offer this system to people and they'll be safe. It has to be trustworthy to the public agencies who will be managing the system as a service to the public. And also it has to be trusted by the society, the users. So in the cyber physical systems, we have the three major components: the sensing, compute, and communication. So these three things are working together: sensing, compute, and communication. But it has to work together in a trusted fashion. So developing a trustworthy system is very important. So one thing I also a big proponent of, that bring the social subject to it, or social context. So because different people will be using the system, and we have people, older people, younger people, like people with disabilities, in different circumstances. So when you develop this cyber physical system, add the word social. I think that bringing in the social context, how people will adopt the system, whether how they will react to it, how they will use it, is very important. Human-machine interface. So when we deploy the cyber physical system, we should think about cyber physical social system. So bringing the people part to our cyber physical system. So we have connected signals and perimeter road. So we can connect with the signals. The signal provides information on signal phasing and timing, and the vehicle can use that information to adjust speed. And also the vehicle data can be sent to the signal controller. So connected signals can help us to reduce travel time on a signalized corridor. And it can help you to platoon connected vehicles. And if you don't have 100% connected vehicles, if you just have few connected vehicles, for example, 5%, but you can form a platoon between two connected vehicles, and in the middle there might be 50 non-connected vehicles. So you can still create a platoon, and we saw that it can significantly improve traffic operations at signalized corridor. So we are doing a lot of pilot studies with connected signals, and I will show one very shortly. So one message I would like to share with you today. I think that cloud system infrastructure is very important for transportation cyber physical system. So the server now at a DOT level or public agency level, it might be very difficult or resource intensive to maintain servers, very sophisticated computers that require a lot of human resources and also money. And also it needs regular maintenance. Also the upgrading is a challenge. So how you upgrade the system you have now. But if you use the commercial cloud, that could be an option we can look at. So we can use a hybrid cloud environment where we use our public agency servers and also use the commercial cloud. So we are doing pilot studies on commercial cloud usage. So now our motivation is that many companies, large banks, large information service providers, entertainment like streaming services, they use cloud, commercial cloud. So one issue I raised by many public agencies is that, is it safe? Because it's maintained by a third party like Amazon, or it is maintained by Google, or it's maintained by Microsoft. But what we know from the industry, so all these large companies, they are using this commercial cloud. It is secure, so not many incidents of cyber attack that is failing the system. But we are also looking at security of commercial cloud. So we have a project where we're looking at that. But I think this is a great option for deploying connected digital system on public roads. So now in terms of the cloud system, cloud infrastructure, so we have different layers. We have the software layer, the platform layer, and the infrastructure layer. So it includes different components. So the infrastructure has database, virtual machine, operating system. So platform, data archiving, computing, streaming and non-streaming services, and software layer where you actually write your code for running the application. So you can have a real-time and non-real-time application. So in a commercial cloud, you can write codes in Python or any other language for your application. So, and you see that it's a combining with different systems, non-transportation services, transportation system, connected vehicles, connected pedestrians, vulnerable road users. So, and we are looking at the feasibility in terms of delay. Now we are trying to connect to a commercial cloud like Amazon or Google. Is it fast enough? So we are uploading the data. It is being processed at the commercial cloud, and we are downloading the data. So can it happen at the same, like in a timely fashion? So what we did, we actually access the cloud for our connected transportation at different times of day, at midnight, at 3 a.m., at 5 a.m. So continuously we try to access the cloud, so to see that whether there is a difference in processing time, upload time, and download time, because we don't know when the transportation system will be on the road, right? So to do the feasibility, we did a continuous testing on the access of the cloud and processing time. So here is another view of the cloud computing. Now this is, the example is with Amazon Cloud, but it's very similar with the Google Cloud and the Microsoft Azure Cloud. So this is the left side, the server-based cloud architecture. So you have a software layer, you have a platform layer, and it's providing different services. And then you have the infrastructure layer. So you have a database, virtual machine, and operating system in infrastructure. But you see that on the serverless cloud, this is missing. There is no infrastructure layer. So what it means that here in the server-based cloud, a user, like if you're a DOT or if you're any other user at a city, you have to maintain this system, the infrastructure. But so that might be a little bit time consuming, and you have extra responsibility. So what we found when we're comparing with server-based and serverless is much better for transportation cyber physical systems. If you're talking about it, used by public agencies or any public agency, I think this is a much better option. So we found that you don't have to maintain the infrastructure. So it is maintained by the cloud service providers like Amazon or Google. So you just, the platform, you access the platform, and then you write the application in the software layer, and it works. So the platform layer triggers the software layer, and then the service inputs goes to your software layer. So for example, it's a connected vehicle data, and then you have the streaming and non-streaming services. It will be continuous data or some historical data or some data from the DOTs coming to your software. It depends on what application you're running. So this feasibility of using commercial cloud, you can see this paper is already available online. So on the, you see the citations, you can see the feasibility of using commercial cloud for any transportation server physical system application. So it's a short paper, but we have some test results that should be very useful. So one example that is depicted in that paper is a real-time cloud-based speed advisory. So this is using Amazon Cloud. So we have these connected vehicles, and we did in real time. We accessed the Amazon Cloud in real time, and then we provided the vehicle trajectory data to the Lambda function. So where we have the application running, and then the Lambda function was processing our algorithm for speed advisory. So which is a combination of connected vehicle data, basic safety messages, and traffic signal and phasing data. It is going to the Kinesis data stream. So it is manages the data stream services, Lambda function where we have our application running. And after running the application, it is sending the speed advisory to all the connected vehicles. So the connected vehicle is sending data to our Lambda function, and the speed advisory to vehicles are coming. The speed advisory is telling the platoon of vehicles what should be their driving speed, so that they will not have to stop at red lights. So our optimal purpose is to the vehicles not stopping at signals. And also the Lambda function access data from the historical database, because we need some historical data to run our application. It could be that the average speed at this time, maybe yesterday, or the day the speed data 1 minute before. So it is coming from the historical database in Amazon Cloud. So as I mentioned earlier, there's a database service in the platform layer. So for our cloud-based speed advisory for connected vehicle in a signalized corridor, COSSCC. So this system that we developed, this is some results that we found. So this is the first graph. When there is no speed advisory, what is the average stop delay in second? So this is the average value for different number of connected vehicles. And what is the delay when we have speed advisory? So the SC-CVT is with speed advisory through commercial cloud. We found that it improves the operation significantly. COSAC, cloud supported speed advisory. And then this graph is showing that average fuel consumption, we see a much benefit with our speed advisory. And this table is showing the delay. So when you have 50 vehicles, so what is the upload delay and download delay with 50 vehicles, the average download delay, and the processing time in the cloud. So the Lambda function is processing information based on the connected vehicle data. So this is the processing time, and this is the total time, end-to-end delay. So the connected vehicle sending data and it is receiving speed advisory. So this is the end-to-end delay. So this is pretty good for a mobility application, but for safety application, we are looking at how to improve it, because the delay should be within like 1 milliseconds or so. But for mobility applications such as speed advisory, and also queue warning, and there are many mobility applications that can be supported by commercial clouds based on our research. So also we are making sure that how we can make sure that if it is our own server where we are running the application from, so it is safe. So we have developed a software. These are the different types of attacks: denial of service, civil, false information, malware, replay, spoofing, and many other. But so the CVGuard is running a software in the cloud, and then it is receiving data from different connected devices, connected vehicles. And if it detects any attack on computer system on the network, it then tries to understand whatever attack it is based on intelligence, and then it sends some micro boxes or small programs or functions to the devices that are being attacked, so that it can implement countermeasures against those attacks. The CVGuard that we develop detects an attack and then implements countermeasures. So that could be something that you can deploy to protect your system. So another important aspect of connected system is the communication. So more specifically, heterogeneous wireless networking. As you can see in this diagram, so this is what we developed for connected system, connected autonomous vehicles. So these connected vehicles are providing data to our system. We call it SDN8, software-defined networking-based handover management. So, and then MPS, a multi-step predictive radio access technology selection. And this is the application database. It knows that what application you're running. So based on the connected vehicle data, what we know of the communication network, so what are the access points available to connected vehicles? And then our software-defined networking is providing direction or instruction to connected vehicles that it should now connect to particular access points. So for example, in this example, we have two access points, Wi-Fi and LTE, Wi-Fi access points and LTE base stations. So our the system age, based on the data that is in your that is residing in your local edge or roadside edge, it is deciding that based on the connected vehicle data, that where the connected vehicle should communicate through. So is it going to use Wi-Fi, or it needs to use LTE? And also the handover, it might be leaving one access point, it needs to connect to another access point. So this handover is very important, because the handover should be like a seamless. So there should be a very low delay between the handover between two access points. It could be same technology like Wi-Fi to Wi-Fi, it could be Wi-Fi to LTE to 5G, but it should be very, very quick. So we use this cloud supported system edge with, based on the data from the roadside edge. So it is deciding that where should the vehicles connect to, and the instruction is going to your connected vehicles. That, but it will, connected vehicles drivers do not have to do anything. It will automatically, the communication radio will switch to a particular access points based on what is available and what is the application requirements. So this is our findings from our heterogeneous wireless test. So as you can see, this is what we developed, this OS plus SDNH. So this, we are optimizing the access point loads here, and we are using SDN, software defined networking, for the network selection. And this is using some predicted mobility data. So the last is the prediction. So you're predicting the location of different connected vehicles at a like a next time scale, next time period. So the first one is we are just optimizing, and we are using our handover scheme. This, the third one is using the handover scheme with SDN, software defined networking, but there is also a prediction. So we are predicting here that where the connected vehicles will be, what will be the acceleration speed, and what the location will be. So that's what we are doing here. And SSF is what is currently used, the signal strength first association. So based on the signal strength, connected vehicles are associated with given access to particular access points. So this is what is used in the industry. But we have developed this optimization-based thing, the strategy, and this is MPS. This is optimization and prediction, and then SDNH. And as you can see, the total handover latency. So what the time it takes to go from one access point to another access point for a connected vehicle is much better with our prediction-based strategy or software we developed. So the same for average total handover latency and average handover latency. And this graph is showing the access point load. So we are trying to improve, optimize the access point loads that are available to connected vehicles. And we can see that with the different numbers of connected vehicles, 20 with just SSF, the traditional system, with the optimization-based system with 20 connected vehicles. And this is with our prediction, optimization, and SDN for 20 vehicles. So we have done with different number of vehicles. But in all cases, our optimization-based system and prediction-based systems work much better than traditional signal strength first association method. Now, the last graph is showing improvement in individual CV packet loss. So it is showing the packet loss for one vehicle at different simulation time step. So this is for SSF, this is for optimization, this is prediction optimization, and SDN. As you can see, this the green box I'm showing here. For SSF, there are a lot of packet loss, but for optimization, there are a few, and there is no packet loss for the prediction-based system that we developed. So we are predicting the location of the connected vehicles, the speed, and then we are using SDN and optimizing the access point load. The packet loss is very, very low. So it shows that using our system we can improve the handover and the load management at different access points. So we're showing this with Wi-Fi and LTE, but it can work with any type of system. You have Wi-Fi, LTE, 5G, DSRC. We can use the same strategy for handover management. So this is what I had today on the digital system for future connected autonomous vehicles, for future connected smart cities. So if you have any question, I'll be very happy to answer. And if you have questions later, or if you want to receive any of the citations I mentioned, I'll be happy to share this with you. So Mahfouz or someone, you can look at any comments or question.
We don't currently have any questions in the chat. We do have a thank you for the presentation.
Okay.
Oh, here we go. Sorry. Okay, so we have a question. What challenges did you face during the real world deployment? And which one do you prefer, DSRC based V2X or 5G V2X?
So, so that's a good thing that we don't know. So we did a comparison. I can tell you that we did a comparison between 5G and DSRC. So we found that 5G is has a more benefit cost ratio higher. So 5G is better than DSRC based on our experiment. So I'll say it, but it will depend. So if you actually implement this heterogeneous wireless networking, it will try to optimize the access point load. So you don't have a load because there are like say 50 connected vehicles, suddenly there are like 200 connected vehicles. So you don't want to overload a 5G station access point. You don't want to overload a DSRC radio. So I see that there could be a combination of systems, DSRC, 5G, LTE, V. So that might be together. And then, so then you can actually decide, or the software can decide what is the best medium to use now based on the access point load. So I think that it will depend on the application and what is available, the signal strength available for different access points. Because if one like access points is being connected by multiple connected system, then that could be a problem. So we have to distribute the load. So I don't think there'll be a one winner. So there could be a, I see that there has to be a network selection, what works best at what time. So I see that it depends on what the application requirements and what is available and the signal strength. And what we are doing, I hope I was able to communicate that when we do the network selection for connected vehicles, we are actually trying to see what is going on, how many vehicles are connected to a particular access point. We are trying to optimize the access point load. Okay, so it's not overloaded. So yeah, so I think that's, but I can just only say based on your research that we found 5G works better for than DSRC for connected vehicle in a corridor. But I would say that heterogeneous wireless networking would be the way to go, because you will not have 5G for like maybe for 50 miles. So it will be covered at a certain section, right? So, but what you do when you go from there. But if a 5G station is already overloaded, what you do? So it has to use something else.
Okay, and we have another question. At the beginning, you've showed different types of infrastructures, including transportation, sensors, CAV, etc. Within these infrastructures, where and how do you see data from data from cell phones can be used? Okay,
let's first answer the first question. So cell phone could be a very good tool. So for example, pedestrian safety. A pedestrian is carrying a cell phone and it is broadcasting, say, basic safety messages from the cell phone with an application. And it is received by connected vehicles, connected trucks, so that it knows that whether the pedestrian will be in a collision path with the vehicle. So the pedestrian can provide data But the only one problem is with the LT service, the delay is not low enough for safety application. So you can use cell phone data like the Google uses for providing information whether this road is congested. We can also do this with our system that, okay, there's a congestion, there's an incident like you get through Google services, right? But so that you can do with this cyber physical system. So cell phone data could be an important input. But the problem is for safety application, current cell phone system is not suitable because of the delay, because the time it takes the cell phone data to go through the LT infrastructure. So I see that with the 5G, you can use cell phone as a safety data source. So the collision avoidance between a pedestrian and vehicles, if you have 5G enabled phone, because the delay would be very low, so potentially that can be used for safety. Right now, I see it can be used for mobility, like a queue detection, something else. You can use the cell phone data that are collected. And what's your second question? So is it clear? So I see that for safety application, you need like a 5G, but mobility, you can use data like Google uses. Okay, is it possible to run a safety application is it possible to run a safety application in the system and collision warning? No, so you cannot do that. So we cannot say, is it possible to run a safety application in the system such as forward collision warning while meeting the delay requirement? No, you cannot do that. For the safety application, like a collision avoidance between two vehicles, it should be between nodes because the delay requirements is so stringent. So it has to be direct data transfer, that when it's through the basic safety message, when it's detecting very close proximity between vehicles, it should be generated right away. You cannot go through system edge. So for collision avoidance, no, it will not be able to meet the delay requirements. So either you have to use DSRC or 5G when it's widely available, because going to the system edge will add a lot of time. Okay. Do you need multiple access points to avoid overload? Do you network? Yes. So Amara, so very good question. Yes, you need multiple access points. So you have to design the system communication that right now there might be 5% connected vehicles connecting, but it might be 200 very soon. So you need to add more access points because if you overload the access points, overload a access point or whatever is available, then packets will be dropped. So although you are sending messages, it will not be reached by another vehicle or another pedestrian. So you need to design it so that you don't overload the system. So you need to add access points. And then, so do the network outage impact? Of course, it will be a serious problem. If the data packets are lost, then you cannot run the application. So, so for example, intersection collision avoidance. So we use this cyber physical system for connected vehicles so that at an unsignalized intersection, they don't collide where we have a side distance problem. But if there's an outage because your access points are overloaded, the application will not work. So you'll have an accident or many accidents. Yeah. Okay, so that's so this is the I think there is a comment from Mahfouz. So there is a citation of a paper. So we deployed this system in real world. So you'll see that this has a very good guidance how you can deploy the system. And if you guys need any help, we'll be able to help you to deploy the system. So it's like, so yeah, we have done it and we have learned a lot. So we have worked on it for many years. So yeah, so there's a citation. Please look at the citation, the paper. And if you don't have access to the paper, we can supply it. Okay,
Right.
so yeah, I see Saurabh. Is it my former student Saurabh?
Yes, Dr. Chowdhury, this is Saurabh.
Hi, how are you doing? So,
Hi,
So the adversarial attack, so you need to, I think you have seen it before. So it is attacking the program, right? So it is not recognizing it as it should with the AI. So you can train the system that, so one way to do it, at the stop sign, right? So it is like you can segment a stop signs into different small pieces. Okay, so because you train the way the autonomous vehicle work, the controller, you train the model, the brain of the autonomous vehicle. Okay, this is what a stop sign look like. It's a red background. This is the text. This is the size. But what some attacker can fool the system, so they know how the AI recognizes a stop sign. So it will provide some parameters that it will think it's not a stop sign. It is a speed limit sign. So instead of stopping, it's asking you to drive at, say, 60 miles per hour, right? So, but one way you can avoid it, there are different ways you can do, but one way we can do it like, so you not recognize the whole system. Okay, each pieces of the stops and you train it in a different way. So it tries to map every single element. So it divides the stop sign into many, many segments. So, and it recognizes by looking at different segments of the stop sign. And also the context. Another is context-aware AI. So, so one way you can do it is segment it. Another is context. So the autonomous vehicle is looking at the environment. So it can know that at this location, you can never have a 60 miles per hour speed sign. So say it's a residential area in a neighborhood, so it will recognize the context, what environment around it. So you cannot have like a 75 miles per hour speed sign on a location that is looking like a 25 miles per hour zone. So it can do that. So there are different ways to do that, Saurabh. So another way is, you have to have a DOT with a very good database. So you can have access to the DOT or public agency database where they have an archive of all the signs and markings and all the traffic control database like SC-CVT has. Mm-hmm. So your autonomous vehicle can access to that database and try to match based on the location that is on your DOT database and what you're seeing now on the road. So the AI may be telling you that it's a 75 miles per hour stop sign, but if you look at the DOT database, you might find no, there's no such thing here. It is a stop sign. So
right.
You can
I guess sorry to interrupt. I guess my question would be, so has there been instances where the autonomous vehicle has wrongly identified? For example, if there was a small scratch mark in a stop sign, and then it said that, hey, this is not a stop sign, or it wrongly identified that this is an adversarial attack where it is not.
So yeah, that could happen too. So if you have a line on a stop sign, so because it just recognizes that the whole stop sign, right, as a whole, so it might recognize it as some other thing. So it might not be an intentional attack, but because of the maintenance, so that it could wrongly recognize. So in that case, also the solution where you are segmenting the stop sign, so you're not looking at the whole thing. So like you are looking at the person, like, so all the different components, like you're recognizing it as a person, not from a distance, not as a whole, but like eyes or like hand.
Okay,
so
makes
you
sense.
can look at different characteristics, right?
Right. Yeah, exactly. It makes sense now.
Yeah.
Thank you.
So that if you look at a whole, you might misunderstand if. Yeah. So, but if you look at the entire, like different components, then you should be fine.
Yes, it makes sense. Thank you.
Any other comment? Okay. Yeah. So I think there's some good information here. So if you are, so Saurabh and some of my former students are in the audience. So what you saw, like you work for the industry now. So I see some of the things we said, the heterogeneous wireless networking and use of commercial cloud. You should encourage your company, either it's public or private, to look into this. Because sometimes public agencies are a little bit reluctant to use it. They think, is it secure? But I have talked to a lot of industry professionals. So they have their many resources, a lot of data in the cloud. They use commercial cloud. So, and they said they have good experience in it. So we need to definitely evaluate, but think of commercial cloud because it helps you not to use the you don't have to maintain, right, the computers. You don't have to scale up. So yeah, so that could be
I think it's what you said is private companies would be happy to move into a cloud-based version, but like you said, public entities there, that's where a lot of things come into stake. So I think that would still be in the long run, like in the future.
But why it has to be long run? Because we have to prepare the public system, the infrastructure, right? So I think it should be sooner. That is, yeah, I wrote a paper, I think with Saki, but I said that we need to prepare, otherwise we'll be behind. So the private industry is advancing with technology, but if we are not prepared, then we cannot.
Exactly.
Right. So my point is, so they're reluctant because probably they have not used commercial cloud. But talk to the industry. Like I know a lot of investment companies, big banks, Netflix, and a lot of big. So they are maintaining their services, their data, everything in the commercial cloud, right? Definitely, we need to look at the security, but they are.
I think that is the main concern, is the security, and it's not so widely commercialized that, and it doesn't have a very, let's say, 1% risk or less than 1% risk. Then maybe public entities would be happy to, or would be able to take that. But since the risk is a little bit higher still, I think that's why public entities.
But if you talk to the industry, the risk is much lower than 1%. Okay, it's very secure. So they are trusting the cloud services with many private data, a lot of things. So yeah, but if you talk to do a survey, do like a study, right? Mm-hmm. Talk to these big companies that uses the commercial server. You'll see that, yeah, we might think it's a high risk. It is not. Risk is very low. Okay. Right. That's what I found out through my research, talking to the industry. And so we are doing a project, Sabir, and so they're involved in that. So we are looking at the commercial cloud security. So we are also finding it's not that it's not risky. So, but if the private industry can, they're trusting the cloud, commercial cloud, and it is increasing. I see a lot of these companies are expanding their businesses, Amazon and Google and Microsoft, because of the cloud services. So it is becoming more and more mainstream in the private world. So I think, I think the public agencies should look at
definitely
it.
I support that. I definitely support that, but I think it's still because of the, like you said, it's even there is like one case of something wrong that went, then the liability, like the public entities would, the liability that they had to go through would be a lot bigger than private when it comes to a private single organization. But, I think that's the whole point. But I definitely support what you're saying. Yeah.
But I think that it should be looked at more carefully. I don't think the risk is higher than what the public agencies deal with. But so I think that let's talk to the private industry who do the service in the commercial cloud, and I can tell you that you'll find different views, that they are trusting billions of dollars, many private records, right? So on the commercial cloud. So, but yeah, let's do just talk to these people who are using it, and you'll see a different answer.
Definitely. Yeah, definitely, I'll do that. Thank you.
That's a perception, sort of. That's a perception, but
it is. Yeah, exactly. Right. You're right.
I found that's not the reality. Okay, so I want to. So Stephen, you like the presentation, but Stephen Deng. So he's my master's student. So he did his research on commercial cloud. So thank you for doing such a great work. So I learned a lot from your research. So I'd like to thank Stephen Deng
very much.
So because he was instrumental on this cloud-based CPS. So thank you, Stephen. And also I would like to thank Mahfuzul Islam and Zadid Khan, who were also instrumental in this cloud application, as well as our superstar, Dr. Mizanur Rahman, who is not here, but he was also a foundation for our CPS research. He was the one who first did the distributed machine learning on cyber physical systems.